As the Sun approaches the peak of its current activity cycle, an interstellar visitor known as 3I, Atlas has begun to astonish astronomers with a sudden and significant surge in brightness that has drawn the attention of observatories around the world. Detected originally as a faint and fast-moving point of light on its way through the inner solar system, 3I, Atlas has now entered the final stretch toward perihelion, its closest point to the Sun. And during the last several days, solar monitoring instruments such as the SOHO spacecraft C3 coronagraph and the GOES-19 SECOR-1 imager have recorded a remarkable transformation. Between October 20 and October 26, its apparent magnitude jumped from roughly plus 10.5 to around plus 7.5, representing a 16-fold increase in brightness, a rate of change that suggests that the object's surface is undergoing rapid physical alteration under intense solar radiation. The cause of this brightening appears to be a combination of factors: the steep rise in solar irradiance as it approaches within a fraction of an astronomical unit from the Sun, the bombardment of energetic particles carried by multiple coronal mass ejections, and the influx of high-velocity solar wind streams that have become unusually strong due to the Sun's heightened magnetic activity. At its estimated perihelion distance, the comet, or interstellar body, will experience approximately 735 watts per square meter of solar energy, a value more than 5 times what Earth receives, and under such flux conditions, the surface materials, ices, dust, and volatile compounds can sublimate explosively, creating plumes and jets that reflect sunlight far more efficiently than the dormant nucleus. Spectral data from ground-based instruments indicate that the brightening is not uniform. Instead, it varies with rotation, implying localized outgassing or fragmentation events. This is consistent with models of thermal stress cracking, as the body heats unevenly while spinning in the fluctuating solar wind. Astronomers emphasize that such behavior is not unprecedented comets like C, 2012 SOHO ISON and 2I. Borisov also displayed rapid brightening and morphological changes near perihelion, but what makes 3I, Atlas, particularly intriguing is its hyperbolic trajectory and its apparent interstellar origin, confirming it is not gravitationally bound to our solar system. The increased energy output detected in extreme ultraviolet and X-ray wavelengths by GOES and Solar Dynamics Observatory instruments indicates that solar flares during this period have likely accelerated the sublimation process, pumping additional energy into the surrounding coma and possibly altering its composition. Its solar storms intensified, with several M-class and one X-class flare erupting from active regions 13,712 and 13,715. The environment around the Sun became a cauldron of plasma turbulence, bathing 3I, Atlas in charged particles that may have stripped away surface layers and exposed fresh volatile material beneath. Researchers are currently using photometric and spectroscopic data to estimate the dust-to-gas ratio in its coma, with early indications pointing to unusually high silicate content, suggesting a dense crust that resisted earlier heating but is now breaking apart. The European Space Agency's Solar and Heliospheric Observatory, which has provided uninterrupted imaging through its LASCO instruments, continues to capture the object's path against the solar background, revealing changes in tail structure that coincide with major solar events. Meanwhile, the Deep Space Network and NASA's Minor Planet Center are refining its orbital parameters to determine how its trajectory will evolve after perihelion. Though preliminary simulations confirm it will escape the solar system, never to return. The physical response of 3I, Atlas, to the Sun's radiation provides a rare natural experiment for studying how interstellar material reacts to intense stellar environments. Its spectrum shows hints of cyanide and diatomic carbon bands, typical of volatile-rich comets. Yet the abundance ratios differ slightly from those seen in solar-borne bodies, implying a distinct chemical heritage possibly from another stellar nursery entirely. These clues are vital for understanding the diversity of matter in our galaxy and for testing theories about the formation of planetary systems beyond our own. Observers using narrowband filters in the optical range have reported short-lived surges in brightness correlated with solar flare timing, indicating that even minor increases in solar flux can dramatically impact the coma's reflectivity. Thermal models suggest that the temperature on its sunward side may have exceeded 600 Kelvin during peak exposure, enough to vaporize complex hydrocarbons and release fine dust that acts as a mirror for sunlight. Despite the dramatic energy environment, there is no evidence that the object is artificial or engineered a speculation that often circulates online when unusual cosmic phenomena appear. Every observation so far aligns with natural cometary behavior under extreme heating. Still, its survival through perihelion remains uncertain. Depending on its size and structural strength, it could either fragment completely or emerge as a dim remnant on the outbound leg. Astronomers are watching closely through space-based instruments since ground-based telescopes cannot observe it while it remains near the sun's glare. Once it moves away, likely by mid-November, follow-up observations will assess whether its brightness stabilizes or fades sharply, which will tell scientists how much mass it lost during its encounter. The interplay between solar radiation pressure, magnetic drag, and particle ejection makes this one of the most complex brightness evolutions recorded for any interstellar object so far. If it survives intact, it could provide critical insight into the mechanical resilience of material formed around other stars. The data from SOHO, STEREO, and GOES will also allow researchers to calibrate models linking solar activity intensity with cometary outgassing rates. This is especially relevant as the Sun approaches the maximum of solar cycle 25, when flare frequency and coronal mass ejection strength reach their peak, creating conditions that challenge both spacecraft and natural visitors alike. The story of 3I, Atlas, is therefore not just about one object brightening in the inner solar system. It is a glimpse into how interstellar debris interacts with the star at full power. Each image, each spectral reading, extends our understanding of the energetic processes that sculpt matter across the galaxy. And as the days near perihelion count down, astronomers remain alert, their instruments tracking every shift in luminosity and tail morphology, knowing that within these fleeting observations lies a chance to decode the secrets of alien material passing through our cosmic neighborhood. Whether it disintegrates or endures, 3I, Atlas, has already given scientists an extraordinary opportunity, a real-time look at an interstellar traveler being transformed by the blazing force of our sun, a reminder that even in the vastness of space, encounters between stars and wanderers can illuminate the fundamental chemistry and physics that bind the universe together.